Sure.
How did you install the environment?
It's a document. So that's where I store.
Since I don't clone the RRA, yep.
But I just found a lot of files. Which one should I use in the?
Oh, after you clone, you need to configure and then install. So there is a README file somewhere there. Yeah.
No.
This one, README. There you go. Yeah, yeah. So there you have the instructions on how to install it. Francis, are you going to discuss the RRA installation? Okay, so he will. Basically, what you need to do is first configure, then do the make, install, and then you will be able to use the library.
So I should use the library. It's which part?
So instead of using the arrays that are embedded in the program, you can substitute those by the ones provided that are arrays. So you have the assignment there. I can show you.
Yeah, so it means that I don't need to create my head file myself. So I just
you will need to create your header file for the functions that you define for breaking into pieces.
Yeah, but my problem is what's the relationship between this program with the...
So the program uses arrays inside, right? They're using these arrays for the number of ants, the velocity of the ants, so there are a bunch of arrays there.
Yeah,
right? So instead of using this way, you can use the ones provided by RRA.
Oh, okay.
You know what I mean?
Okay, so
first you need to install RRA and then substitute those with the codes for RRA.
So and I still need to separate them into different models.
Exactly. And then
use this function, use this array or the array from RRA.
The idea is that you use the ones from RRA.
Okay.
So it says, there are several steps. Actually, one is breaking the code into pieces and then putting these pieces in modules, meaning a header file with different files for each function.
So the module is not us, right?
No,
so I don't need to write a class.
You don't need to write a class.
So I just made them separately and use a make file to compile.
Exactly. Okay. And there are some comments that Rance is going to do right now regarding RRA and regarding the make file.
Okay.
So it's, no problem.
Right. So you could. So just anything that does an output should either be, so the time step should be separate from the, should be different time steps. Yeah, no, it is a puzzle. Try to find the.
What are they called?
Yeah, just do like this for now. What time is it? Oh, it's not. Oh, it's even later. Okay.
Yeah.
Yeah, we can start this. I mean, it's. I don't want to take too much time away from the lecture. Thanks.
By the way, with the homeworks being graded, and how well we did or how well or poorly we did on
This afternoon.
Oh.
Yeah, I'm just gonna put it up. I checked Hangout. Yeah, it's working.
That is a mute.
It's
a mute.
No, it's not on mute. Oh no, I heard stuff. Yeah. Okay. Okay, so while we're setting up, I thought I'd go over a few clarifications about the assignments, and we'll post this on the website too for those who are coming in late, but just to go over them. So the assignments, one, have been graded, or at least the ones that are already in, which is most of them. And this afternoon, I'll probably put them up with feedback as well as your grades. The feedback will be in the same section where you uploaded your file. So probably attached to the first file, I'll give all the comments. And then there's a separate tab for grades. If you've already noticed on the education side, there's now a gradebook tab that you will see your graded. So I just want to go over a few mistakes in homework 1 so that you can already not make them when you submit your homework 2 and just be ahead. And some of these are just about submissions, things that aren't so much wrong as misunderstandings or So a few things. One, please don't use file names without spaces. When we start automating and using makefiles for real, spaces are going to break your makefile. So it's not just that we don't like them and they get in the way of scripting. And if you know that, there's no reason to use spaces. Use underscores if you must separate your words. Another thing that I noticed confused some of you is I said to upload your files in text format, but it doesn't really mean that they have to be renamed to something that ends with .txt. Text format just refers to what's in the document. There's no special codes that come from Microsoft Word or something like that, just plain text. But they can still be called .cpp, .cc, .cxx. And so when you upload them under the name that you use them under. And it's especially important when we try to reproduce your compilation, because your compilation line would have said G++ something .cc, not .txt. And so I had to rename your files to get that to work. And this is going to be even more tricky when we do make files. We have several files. So please just upload them under the name that they had. And then make sure that when you save them, and then if you have a code editor, it's going to save in plain text. But if you write like your reports in Microsoft Word or something like that, don't save them as rich text format. Those are not text. Those are not plain text. They have all kinds of codes. That's the rich part. So plain text, those you could just save as .txt and you'll be fine. And then finally, don't submit the executable that you built. It will probably only run on your machine and any machine that's exactly like your machine. As long as the build procedures that you give us a running executable, that's good enough, and that's exactly what we'll test out. Okay, so there's no need to submit those. Then the actual hardware matter. So most of you did very well. Okay, so let me just say that. I don't think I've seen any poor ones. Just a few fine points that were common to some of the homeworks. We asked for 100 numbers to be outputted, and many of you got to 101. So that's an off by 1 error. This you could say that's not so bad because you get more than when you ask for. But if this is a part of a larger program and the next step requires exactly 100 points, it wouldn't work. So just to be precise, when there's 100, it should be 100. And if this is because of your loop and it did one more case than you thought it did, try using an integer as your counter for a loop to make sure you do exactly the number of points as was requested. If the request was to go up to 5, rather 5.0 in x values, that would be different. The 101 would have been fine, but we asked for 100 numbers. Another thing that a lot of you did, and this is actually not bad, we wrote out our data in text format. A lot of you felt the need to have the first line say what the different columns mean. Excellent. Except now that looks like code to things like programs that plot your data. So to sort of signify that this is a descriptor rather than data, sort of a common practice is to put a pound sign in front of the first line. And the pound sign has disappeared from the slide because it has a special meaning in LaTeX. Anyway, so started with a pound sign, so a number sign. Then if you're compiling anyway, and since we're going to do scientific computing, just put .o2, make sure that is a capital O, as optimization as your default. Once you start debugging, which we'll talk about today, you will take that off. But for anything that's production code, that should be your safe default, unless you have a really good reason not to do it. Then another thing in codes is when you have constants. I saw some people using the old pound define structure to define constants. That is an old style C mode, which it's not that it doesn't work or that it's particularly bad, but we'll just prefer const variables, mainly because those can check whether your variables are actually of the right type, so that you don't use a string where there should be an integer, and with pound define you don't have type correctness. So prefer const. And then finally, if you can help it, don't use global variables. The const might be occasionally the exception if you have true constants that are used everywhere, but any variable should not be global. And the trouble is with global variables is that every part of your program can touch it. And if every part of your program can touch it, it means that every part of your program can cause a bug in that variable. If a variable is only lives in one function, that cannot happen, and so you sort of safeguard yourself. Okay, so that's what happened in homework 1. I'll post the results of your markings this afternoon, and then if you have more questions, just email us back that, hey, I don't quite understand what you meant with this. The point here was to get everybody a bit up to speed, and I was impressed on how well everybody. Yeah. So if you have a question, I know there's a comment section to the comments. We don't tend to look at that, and there's no way to automate an email. So just email us directly at courses@signet. Okay, and then homework 2, quickly. Some people asked about what we mean by the git log that you have to submit. So when you type in git log, you get a log of all the commits that you've made. If you do -stat, they'll also tell you the differences in each of the commits. Dump that to a file. So this you can in Bash shell you can just redirect with this >, or copy and paste it from the terminal. I don't really care how you get the output, but get that output into a file and submit it with it. And then especially Mac users have had some issues with installing the RRA library. This was partly due to RRA itself, and so we've fixed and made the configure script more robust so that if you go back to the directory where your RRA was originally cloned into and you do a git pull, you will actually get the newest version. One of the nice things of Git, and it'll only download these things that have changed. And then you can reconfigure things if you use the configure and make install. Configure is actually optional in this case to install things, but it'll test whether you have a working compiler, etc. And that was the part that actually went wrong. And make install will now work as well. If you have sudo access or you just want to install this for the whole system, sudo make install will do that, and it will make things easier. If you can't do that, or you want to put it in a separate directory, use this prefix equal basedir. That puts it in basedir/include. And this is something that we'll see more when we're using other libraries, but you'll have to tell the compiler where this directory lives. There's a -i for include, capital I, basedir/include is what you would do. So you substitute basedir for any directory that you have write access to. You can save it anywhere. The only thing that matters is that when you install it, you add this option so that when you compile. So this could live somewhere else from your code, and I don't want you to submit the RRA stuff either. So your code is there, and it finds the RRA library just by this one option. If you do it with sudo, it should find it automatically without the option.
So basically, that doesn't even install RRA on ours. Don't put that in. You try compiling.
Yeah. So this one's going to be one which breaks me trying to do it. But since I will also have it installed in a standard location, it'll just go, okay, I'll use the one you have. So if it works with this, having an extra directory to look in is not going to break things when right, that's not going to break things. It'll just look for it elsewhere. If you want to do so, not for the installation and not for using it, but if you want to, there's some tests that are in the makefile, and to run those, you would need boost test, which we'll talk about today. And it also has benchmarks to compare it with other array libraries like Blitz, Eigen, one more. And so if you want to use those, you'll have to have those libraries installed to do the benchmarks. But you don't have to do that for homework. No. The boost test is something you should install at some point anyway, probably after this lecture. But for this assignment, it is not needed. Okay, and then finally, if you still need help, the old email still works. Office hours are still available. But all of you have found the forum, sorry, you should have said forum, not chat. The forum where you can ask questions. And the nice thing is you ask a question there, you can all see it and answer to it too. So if you already know the answer to a question of one of your classmates, you can beat me. This has happened already. But I try to set up email notifications so I see when people ask a question. You can do the same so that you can see when you get an answer to your question. So it's a very handy way to get a fast response, because I know some of you do your homework at night and I might just be sleeping. That's right. Yeah. And it's just nice to look at too. Just if you have a question, you can see what's this asked already. So like with the RRA installations, there's a few points that came up there. Okay. Yeah. That's right. Like the number of steps, the number of grid cells that you have, or the dimensions of the array. The idea is that at some point you might want to consider a bigger table with ants, and then you don't want to change it all over the place. You just want to change it in one spot. Yeah. Right. Yeah. Oh, let me show it to you. I think it's open. So on the side, I did that. Because we're in the chat. Yeah. So there's a forums here. You have to be logged in to see it, but then, and for some reason you click twice, but here are all the posts. And so you can create a new thread if you have a question, and just all you have to be is logged in. You're all on the system now. So okay. Good. Time for the actual lecture then.
Okay. So Francis mentioned a couple of interesting points. We're going to discuss them today, like having an array or an index that goes beyond the bound of the array. Other things like optimization flags and the boost library. So today, what we are going to discuss is debugging, basically finding problems in your code and testing the modules, the units that we talked last week or week before. So the plan for today is just describe some basic debugging techniques, some of the tools like the command line debugger, GDB, a memory checking tool that is very, very nice. We are going to use Valgrind also for performance in next class, for testing performance. And finally, the Boost unit test framework that is part of the Boost libraries. So why debugging? Well, basically, it's very tough or very difficult to develop a program without having any bug. And what by bug, I mean an error that may show up in your computations that you may be aware and you are fighting with it, or maybe not. That's actually the most tricky and difficult bugs to catch. So you may have a situation like this. You compile your program, you execute, and you get a segmentation fault. Actually, you should be happy because it's an indication that something bad is happening with your code. What doesn't happen is miracles, especially in science, right? So without any interaction that the program works again, it's very unlikely that happens. And actually, if that happens, you should be suspicious of what could be going on with the code, right? So basically, debugging is a method of finding and fixing flaws in your code, in your software. One thing that everyone should keep in mind is that usually programs execute correctly in the sense that they do exactly what they ask them to do. Okay, so if something goes wrong, it's probably our fault. So somehow, debugging is just not a dry technique; it's an art of reconciling the mental model of what we have in mind that the code is doing with what the actual code is doing. What is a debugger? Well, it's a program that will help to detect errors in other programs. The truth is that the real debugger is the person running the program, because it's the person who has to analyze what is going on in front of you, right? So there are some tips to avoid or reduce the number of bugs. This is really, as I say, it's very tough. You have been coding, you will know this for sure. It's very tough to develop code without any kind of bugs. But things that may help to avoid that is write simpler and clear and straightforward code. Use modules. We talked about that last week, and we are going to see how to test those modules today. And debug a module or a small unit is way easier than debugging a code with 10,000 lines. About Qtrix, especially in C and C++, it's a very cryptic language. It can turn into a very cryptic language. There are actually websites like the one there, IOCCC, that show very, very cryptic piece of code that you have no idea what the code is doing, actually, right? So by avoiding those kind of things, you can write a cleaner code and easy to understand. If there are things that are already created for you, especially libraries that find solutions or resolve situations that you had to tackle, use the libraries. Usually they have been tested, they have been debugged by other people. If it is widely used, probably people have find bugs. So it's a nice thing to do. Write always simple tests for each of the parts of your code. I know that sounds like painful and a waste of time, but it is not. It will help you actually to develop better and a more clean code. How the debug workflow works. As soon as you know that there is a problem, you need to try to recreate a situation where the problem shows up. Basically, it's like a test case where you know, or you expect to know the result that that situation will return, and try to test for it. If you know the solution for a given equation and you are solving that equation, try to get that simple solution. We do that in math, right? If you are solving a differential equation, you want to write the analytical solution, and you know a particular case, you test your solution against that. So this is basically kind of the same idea. Again, it may sound like an art, it's part of art, but it's also science. So try to create a model of what is going on, try to hypothesize what is going on, try to reproduce, experiment what is going on, and try to draw a conclusion where the problem may be. If it is a code that is dealing with complicated situations, try to always find a simple case to try, a small problem size. If you are dealing with complicated physical situations like non-linearities, try to turn off the non-linear part so the solution will be smoother. It may depend on the problem itself, but try to simplify the problem at its most. If it is possible, even try to narrow down the problem to the module, function, or class that it is showing up. If you are doing integrated calculations, these are examples, but if you are doing integrated calculations, try to write out intermediate results and inspect them. And this is kind of borderline with something that we're going to discuss, that is print statements. I'm going to talk a bit more about that. Before that, some of the kind of errors that you may get. So there are errors at the compilation time. So basically, you try to compile your code, and something happens, and you get an error. Those are not so bad, because basically the compiler will give you information. So you can have syntax errors. These are easy to fix. Basically, it tell you, okay, I don't recognize this command. It give you the line. You go there to fix it. It can be library issues. Probably already you have experience with the RRA library. Those are a bit more tricky, perhaps, but it's also kind of simple to fix. Basically, you need to do the linkage with the correct library options. Cross-compilation things is when basically you have a code, you have developed a code like in a Mac, and you want to run in a Linux box, and the code doesn't work because there are some dependencies with the OS or something like that. It's not so common, especially nowadays, but it may happen. And then compilation warnings. Compilation warnings usually is not so good practice, but people try to don't take or not pay too much attention to them. But basically, it's always a good idea to take a look at them and be sure I understand all the warnings that the compiler is giving me. I'm safe to go. But pay attention, look at them, because sometimes they give you some insights. How you activate those compilations warnings? Well, my suggestion is to use -w all, which means that will show all the warnings. Okay, so when you add in the compilation line or in the make file, you can use -w all. The other thing that may happen is, okay, you have a code that is compiled, it ran, but it still may have bugs, and the results may be not correct. So this is where we need the test cases. The other type of errors that you may get is runtime errors that happen while the code is running. Okay, so you get your executable, and now you can have these other problems. Floating point exceptions are problems that you may get when you do your math, like divisions by 0 or square roots of negative numbers. Segmentation faults may happen when you try to access memory that is not part of your code or is not associated with your structures, or you may go out of bounds in an array. An abortion can be a more serious problem with the code. It may be maybe it's also a segmentation fault, but it's trying to access memory from the system. And then the other thing that may happen is that you have incorrect outputs, like nonce. Nonce means not a number. So some compilers, I think GCC allows for nonce. So you may still produce some outputs, but it may all nonce, or some of them will be nonce. So there is clearly something obviously wrong. Okay, questions so far? Yep. So the floating point exceptions is when you may have some kind of math that doesn't go well. Like if you try to divide by 0, you may get that, or a square root of a negative number, or the logarithm of a negative number, those kinds of things. It's associating with the representation of the floating of the number as floating. Okay, so other common issues that you may find, again, in arithmetic, you may have corner cases. Like if you try a square root of -0.0, depending on the compiler, you may get a 0 or you may get an error. Okay. Also, if your numbers go beyond the representation of the type of variable that you are using, you may get an infinity. The memory access is something that we mentioned. An index out of range, for instance, or initialized pointers. Okay. Logics, these are very cute ones because you can stay in loops forever, right? And deals a bit with what Francis was saying of be careful with the index of the loops that you use for. If you don't meet the conditions, you may stay there forever. There is a nice combination of these logic errors with the syntax errors. Imagine that you are doing a for loop and you are using a new variable I that you define there, but instead of asking for the condition I equal, you put I equal to something, and that loop will go forever because the equal condition doesn't hold ever, right? Just do an assignment. What else? Resource starvation. That is something that we are going to see today, like memory leak or overflows. And then when we probably discuss parallel techniques, you will see that there are problems like race conditions where two processes try to fight for a same resource. They try to update a variable, but the other updated before, so the results may not match, or at the low where both are basically standing by for permission to access something. Okay, how we can debug. There is a preemptive way. As I say, it's always a good idea to turn on all the compiler warnings. So use -w all, it's warning all. Another way that you can actually include in your code is using asserts. Basically, assert is you have a variable that you know that has to be positive, so you can put an assert command in your code. I don't remember if we look at that in the intro, probably not, right? Okay, we may include an example here again later. So basically, you can actually check for the variable to be greater than 0. Okay, it's a nice trick actually. I can tell you for finding nonce. So you can always do this. So let's say x is a variable, right? And what I'm asking there is to be sure that x is equal to x. Obviously, it's always the case. Well, it's not the case if x is a NaN. So one NaN is never equal to another NaN.
So assert function.
It basically will guarantee you that x is not a NaN. Otherwise, you know that you have a problem with the variable x. Okay?
It's not. Or
It
the
applies.
program tells you this is the way of catching.
So it's like a stronger.
Yeah.
Well, actually,
Yeah. It's supposed to be for things that you are completely sure that they should be true. Like a variable should be always equal to its variable itself, unless that there is something wrong and it's a NaN. Okay? Or the argument of a log function. It should always be greater than 0, right? If that doesn't hold, the log will have a arithmetic problem, right? We talked about this at the very beginning. Inspect always the exit code. So you suppose that if everything went well, the exit code of your code should be a 0, right? So you do echo $0 and you should return that value. Finally, if you are still suspicious that there is a problem, use a debugger. And of course, you can always think about adding print statements. Who hasn't done that? I have. So everyone at some point in their life do the print statement. So what is the problem with the print statement? I will tell you. It's basically a vicious cycle. Okay. So what is the strategy of the print statement? You add so there is something wrong with your code. You may get nans. You don't know exactly where. You add a print statement. You compile the code. You run the code. You analyze the output, and you don't find the bug yet because there is not much clue, right? So you come back and repeat and repeat and repeat until you narrow down where the probable bug is there, right? There are a couple of issues with this. One of them is, well, yeah, you may be lucky and find the first bug, and you may have more bugs probably, and you will have to repeat this again and again. So first thing is it's quite time consuming. If your code is complex enough that you need to spend some time, you will spend a really good amount of time. The other problem is, and these two are kind of combined, the error prone and change memory, is you have a very serious issue like a pointer or going out of bounds. It's very difficult to catch those kind of bugs by adding print statement, because in some cases it may run just fine, in some cases it's just not run. Okay, so that is it's very tricky. It's very tricky to find bugs associated with allocation of pointers or going beyond bounds in the arrays by just adding print statement. Okay, so the better way is to use a debug. Okay, any questions or comments? Okay, so usually it's called symbolic debuggers because it's analyzing the symbols within the program that you want to analyze. It can inspect crashes of the code. It has the stock of the functions that are being called. It can step through the code. It allows you to put like breakpoints, automated interruptions, so you can tell the debugger, go until this line, that I'm pretty sure everything is fine. Stop there, analyze, and continue. It allows you for checking the variables, the values the variables store, and actually to set the values. If you are suspicious that something is triggering the error, you can actually set the values of the variables and try to run with those within the. I'm going to see a particular example. There are different types of debuggers, depending again on the platform. You may have different ones. There are basically the big vision here is to have graphic user interfaces debuggers or text user interface debuggers. In your workstation, in your own laptop, using a graphic debugger is okay because basically it won't be such a problem with the speed of the code. But if you are doing remote debugging, let's say that you are running in the cluster in Signet, if you try to use a graphic debugger, it can be slow because of the complication. But you can still try. But basically, what is happening behind the scenes is the same. So the same concepts and ideas work either for a graphic or text-based debug. One thing that we need to do before debugging is to prepare the executable for being debugged. And we do that by adding some particular flags. The flag that allow you to debug, and it's useful because it includes the symbol, so you can actually access the variables with the name that you have given to them, is the -c option, the -c flag. Depending on the compiler, you may have other ones as well, but in general, -c allow you for adding the debugger symbols. And the other thing that is usually recommended to do is to switch off the optimization. So Francis was mentioning at the beginning that nowadays most of the people use -02 for the optimization. So there are different levels of optimization, 1, 2, and 3. 3 being the most aggressive one. 2 is a good relation that you can keep. 0 is no optimization at all. And why we do that? Because when we turn on the optimization, the compiler tries to do smart tricks, try to replace expressions within the code to make it run faster, right? By switching off the optimizations, we are telling the compiler, don't do any trick. Just leave the code as I wrote it. Don't substitute anything, so I can debug it in the way that I wrote it. Okay. So remember, -c and -00 when you try to debug. Yep. It may depend on the debugger, you know. On the compiler. Yeah.
Optimize, but the Intel compiler is second line. They'll optimize by the, so it just depends.
Yeah.
They used to just be.
Yeah. It's always. So the tool that we're going to use is called GDB, which is the new debugger. It's free. It's usually installed in all Linux systems, and if it's not, you can install it. So, as I said, it's a new license symbolic debugger. It's available in many of the systems. It has been around for a while, but it's still developed and supported. It has a text-based interface. You have to add the -TUI for text user interface option. If you are running on Signet, and I have an example here how to run it, how to compile and how to run it. If you are running on Signet, you probably are familiar with these lines. If you're going to try in your own laptop, forget about the module lines. So if you want to try on Signet, you have already your Signet account, you can do module load GCC if you want to use the new compilers, or module load Intel if you want to use the Intel compilers. This is the compilation line. This is an example just. So you use the compiler, the -c for the debugger, and -00 for turning off the optimization. The source, the name of the source file, -o, the name of the executable. Okay. Again, this is a line specifically for Signet. If you want to use the debugger, you need to load GTB. So you do module load GTB, and then basically you just start the debugger. GDB -TUI for the interface, and then the name of the executor. Okay, and basically we'll load the program for you, and the prompt will look like GDB between parentheses. That means that you are in the interface of the debugger. Okay, but basically you need two steps. You need to compile with the debugger options, with the -c and turning off the optimization, and then execute the debugger with the executable that you want to analyze. Okay. Here is a summary of the functions, some of the functions the debugger allow you to do. Of course, there is a help. Run will execute the program. Backtrace, it will show you the function call stat, basically all the functions that have been called at a certain point in the program. We're going to see this in more concrete example within the code, but just to give you a summary in advance. Break will allow you to set these breakpoints, so you will mark a line or a function within the program up to up to the point where do you want to reach without interrupting. Delete will allow you to delete these breakpoints. Continue is continuing the execution after you reach the breakpoint. So you reach the breakpoint, you can analyze the variables, you can see the variables, you can set the values of the variables. You set the breakpoint to the line where it's going to interrupt. Stop before, yeah. So you just reach that line. It's not execute when you can. After you reach the breakpoint, you can actually advance by a step. You can, if it is the call of a function, you can just go into the function or execute the line without calling the function and get the prompt after back. So there are many options, but you execute up to that line and then give you the context. As I say, there is next and a step. Print will print you the value of the variables. If you want always to see the value of a variable, instead of using print, there is display. So it will show at each step the value of a given variable. Quit is for quitting. And what else? A bunch more. Let me show you with examples. It will be clean. Set variables is useful because it allows you to change the value of the variable. Temporary breakpoints is just execute the breakpoint once and then goes away. Watch is the one I was talking. So you can watch variable and it will display at every time values that. There's another thing that you can do with the debuggers, which is inspecting the core files. So one thing that may happen is when you run your code and your code crashes, it may generate a core file. A core file is a file that contains the state of the memory at the moment that the file crashed, that the code crashed. So basically, by inspecting that file, you will basically reproduce the state of the memory at that exact. One thing that, so not always you will get a core file. And one of the reasons that you may not get a core file, if you haven't set an environmental parameter in the operating system to have a big enough number. So basically, it's the size, the maximum size that a core file can have. You can inspect the value of several of those by typing ulimit -a. So ulimit stands for upper limit. So it will display you if you are in a Linux or Mac or mobile. I think it may work probably. If you just type ulimit -a, it will show you a set of parameters and values. You can set, in particular, the size of the core file by typing ulimit -c and the number, and it's in bytes, I think, kilobytes. If you are not sure, and your code may be generating several variables and a big core file, you can use ulimit -c and limit. And basically, that will allow to create whatever size of the core file. Okay. The GDB can read those core files, and the way to do it is you use GDB, the name of your code, and the name of the core file. And basically, it will start in the place where the code crashed. So there you can inspect the values of the variables. You can try to continue executing, or you can try to go back. As I say, if you don't have a core file, first of all, check the ulimit value. Maybe that is set to 0, so there's no possibility of creating the core file. But if you are not interested in looking at what happened with the core file, or by inspecting the core file doesn't give you enough information, what you can try to do is to run the code within the debug. So that's what we are going to do now. Basically, you start the debug in the same way as we described before, GDB, the name of your code. And then within the GDB interface, you type run, and the program will run. It will stop at the moment where it crashed, and then you can inspect what happened there. Okay, questions? No? So this is an example. It's a C code. What it does is very simple. You will see that this code has a couple of bugs. Some of them you can basically find by just looking at the code. I bet that some of you already did that. But forget about that we are able to identify those bugs by just looking at it. We are going to try to find these bugs by using the debug. Okay? So what the code does is it creates an array, and it fills with basically a numerical value that is given by the square root of an argument that is part of the index that is looping on, and then is computing the sum of these squares. Okay, just a loop here. It's filling the values in the array and is computing the sum. Okay, and then at the end it's printed and it's returning a 0. Okay, so it's a very simple code. Let's see what happened. I'm going to. Oh, the other thing that it's doing, I don't remember if we mentioned this, is reading from a standard input the value that it should go up to. So n max is the maximum number of numbers of integers that we'll cover in this loop, and it's reading it by a standard input. Okay. So what will happen is I will compile my code. I will use -c. I'm giving the name of a square. I forgot to add the optimization equals 0 without optimization meaning. And then what I'm doing is running a square, and I'm typing 5,000. And the first thing that I get is a segmentation. Okay. So remember what was a segmentation? What kind of indication was a segmentation for? Sorry, again. It may be related to that, but the segmentation for was, yep. Yeah, that will be my suspicious. I don't remember exactly the example, but that will be my suspicion. So what I should do now, or what I will do, is start the debugger. And there was, so this execution generated a core file, and the core file has a number. It's the process ID number. So every time that you run something in the system, there's a process ID associated with that process. So basically, the core number is that the name of the core file is core dot and the process ID. So what I'm going to do is start the debugger with the name of the program and the core file. Okay. Yep. Yeah. When I run a square, I type 5,000 in the keyboard. I press enter. It crashes, giving a segmentation fault because I have GB limited -c unlimited. It generates a core file. Okay. Yeah, it's just the process ID that. So every time that you run the code, it will have a process ID associated, and the core file will have at the end the number of the process ID. Okay. So when I do this, when I start the debugger, the first thing that it tells me is, well, the program terminated with signal 11, which means a segmentation fault. So each signal in the shell has a meaning, and this is the meaning. It's giving me an address in hexadecimal, because it's not too useful. But then it's giving me in the line of the code where it fails, and it's showing that line. Okay, and basically that line is here. And as someone said, that is very likely to be associated with accessing the array out of limit, or trying to access memory in a part that is not part of the reservation. Okay, so that's point us towards the first path. Okay, so I may be trying to access the array beyond the limits of the array. Yep. So if you are executing, if there is a core file, it is in the same directory where you execute the file. Okay, so let's say you are in your home directory, you execute this program, and I invite you guys to try. You can actually copy and paste, so you can reproduce this example, or I can upload the code if you want to the website. But basically, you can compile this and try to execute, and you should get a core file in the same directory where you are executing this program. Okay. It's a nice code because it's small enough, but it has several bugs. So it's a nice code to try to catch them by your own. So that's the first thing. Okay. Let's take advantage of this example to look into the debugger itself and some functionality. If you have the code running and it's in a loop, for instance, and you want to interrupt the code while you are in the debugger, you can press Ctrl+C. That will interrupt the execution of the code and will return you to this GDB prompt. And the debugger will show you in which line it was interrupted. One thing that you can do is what is called stack trace. Basically, is is telling, or the debugger will tell you the list of functions that have been called at that point, okay? And what were the arguments of the functions called. So you can do backtrace, and we'll show you the function call stack, basically this list of functions that have been called. Imagine that you are in a code that is complicated enough, and you go into a function, and that function call another function and another function. It will use that list. Then you can do continue for keeping executing from that point on. You can go down to go to the called function, or go up, go to the caller function. I think we mentioned this, but we are allowed to execute line by line by typing a step. You can go into the functions itself, and if you use the -t UI option, it will allow you to see lines up and down before the current line. So it will show you a neighborhood of lines or surrounding lines to the current. If you type, these are another commands that are useful. It was in the list of the summary, I think. List will show you a partial list of the code. So you can actually do list and a number, which represents the number of lines, and I think show you 5 lines up and 5 lines down, I think. Next, we talk about that, the steps. It allows you to go into the function. Finish, if you are in a function and you type finish, it runs until the end of the function. So you're sure that the function is fine. You want to just move forward, just type finish. You can do conditions. You can use until, and you run until certain function is called or certain line is called. Okay? I'm trying to mix a bit the functionalities with some examples. I promise I will have another example. Breakpoints. Breakpoints are really, really useful. So you can put breakpoints in lines or functions. So the debugger will execute until reaching that breakpoint. You can add several conditions and several breakpoints, and you can have temporary breakpoints. These are some of the commands related to the breakpoint. Delete will delete the breakpoints. If you don't want to stop there anymore, you are inside a loop. And yep.
Break start.
It breaks at the before executing. It's like you can put conditions to execute the breakpoint. So if a given condition is called, then the breakpoint is executed. You can disable breakpoints, so meaning you don't remove the breakpoint, it's there, but you don't want in this time to take care of it. You can enable the breakpoints. You can get info of the breakpoints, so it will show you all the breakpoints that you have up, and you can have them. The other interesting thing and very useful is to play with the values of the variables. So let's say I'm having problems with a function, and I think that is the value of the argument of that function. So I can just change the value of the argument. So I can try to inspect what the value of the variable is. I can keep track of the variable by displaying any time. I can stop the program when the variable changes. And as I say, I can set the value of the variable if I want. So these are the options for that. Print, and the name of the variable will show the value of the variable. Display will print at every time. Set variable will change the value, and watch will display only if the variable change. So that can be okay. So I show you some of the commands. Let's come back to the code. So we saw before that there was a problem with the memory, with the access of the memory. My guess is that the problem was that, as you see here, the squares array is a dynamic array, and I wasn't allocating memory for it. Okay, so the line I added now is a line for allocating the memory for the array. Okay, and the number of elements of that array is n max. Okay, so there was a segmentation fault. You come back to the code and you can see, okay, there wasn't actually any memory associated with the array squares. Okay, so let's try it again. I recompile the code, and now I'm executing in the debugger again. Let me show you what happened when you do list 15. List will show part of the code. So it will show from the line 15, 5 lines up and down. And this is how the code looks like. Now I would like to set a breakpoint. What I'm going to do is set a breakpoint in the line 13, is where the addition of the values of a square is happening. So it's sum plus equal squares of I. Okay? And what the debugger says after I type break 13 is, okay, there is a breakpoint and an hexadecimal position, but basically it's at the line 13 of the code. Okay, so I set a breakpoint there. Now I'm going to run the code. I just tap and run and enter. Okay, so starts the program. It's asking for the input, so I type 20, for instance. And it says, okay, I reached the breakpoint number 1, which is at line 13 of a square, and it's showing the line. And one thing I can do is, okay, I want to know which is the value of sum. Okay, and sum has the value of 5.888 something to the minus 39. Okay, remember this line hasn't been executed yet. I'm going to do one step. So I'm within the loop. So I'm going to do one step. So it comes back to the loop, to the forefront of the loop. And now I want to know what is the value of sum again. Okay, and the value is a none. Something clearly go wrong there. I want to know now, because basically sum has the value of a squares of 0, right? As I said, this code is very simple, but you see the logic behind. And a squares of 0 is a none. And if you look, go back, wasn't smart. If you look at the line where the squares of I is assigned, it's taking the square root of I minus 2. And the 4 is starting at 1. So the first element that is trying to assign is a square root of minus 1. Okay? And in this case, I was using GCC, so GCC will allow for nulls. It will tell me, oh, the operation you are trying to do is illegal, right? No, that's why I try to do by step. So when I do gdb.square, I type enter, the thing that I'm seeing is gdb. That's the prompt of gdb between parentheses, okay? The next thing I do is I type list15 and enter. And what shows is that. It's the command that I'm typing and then the result. Okay? So this is another example of how to find another kind of path by inspecting step by step the code itself. I promise you there are more bugs in that. Let me just very quickly show you a couple of slides about how graphics debuggers looks like. They can be nice because they offer a more intuitive interface by having mouse control over the code. You can just double click on the line and will pop up a breakpoint for you there. But it's the same idea and the same concepts. They need graphics support, so if you are doing this remotely, you need to use either a BNC connection or port graphics using X4. If you don't know or you're not trying to do, don't worry too much about that. But the reason I'm mentioning is when we are going to do parallel programming, there is a very nice tool which is called DDT that is a very nice debugger for parallel problems. So it will help you to find race conditions and deadlocks and other kind of things. Okay. If you are using SciNet, these are the lines that you need to execute. Again, you need to load the module systems. You will need the compiler. And in the first case, it's a very old but free graphic interface for GDB. It's called DDD. It stands for Display Data Debugger or something like that. It's pretty cool because actually, I don't know if it is very useful, but it's cool. It allows you to make plots of the variables. So you can do a representation in graphics of the value of the variables and see graphically if it's just changing or not. And DDT, as I say, is a commercial one, but it's very good, especially when you try to debug codes in parallel. If you have access to SciNet, you have access to DDT. Okay, so I invite you to try it. and it runs in the same way as sheet. Yeah, actually, in the back end, at least DDD is using sheet. Okay, DDD is a bit more complicated. This is how they look like. This is the DDD debugger. It's a bit old style looking, but it's old, so that's why. You can see there is a floating menu there with all the commands that we discussed before. As I said, you can double click in the line and it put you breaking points. There's the watch, stop. There is the plot. They are in the top panel, so you can create the plots of the variables. It's pretty nice. This is how DDT looks like. It's way more complicated. In this case, there is a code running in 4 threads. You can see in the blue line there, 0, 1, 2, and 3 is the threads that this is the code running. So it allows you to do this kind of parallel debugging. It's a pretty nice tool. So, oh, really? Okay, happens all the time. Okay, so we are going to stop here. Next class, we continue doing debugging on memory. Okay, Nick? Yeah. So, any questions? You can take a look at the code. I promise there will be more bugs there. Okay. Oh, by the way, something I forgot to mention. 2 things, but we are just past 12. So, first thing is tomorrow we have the intro to Linux shell at SciNet from 10 to 1. So if you guys are not too much experienced in Linux, I invite you to go there. Just go to the website, to the education website, register there, is for free, and you get some credits towards the certificate. Yep.
I have a few questions about like assignment 2.
Sorry?
I have a few questions about the assignment 2.
Sure. Give me just one sec. Let me stop the thing. Yeah, sure. Sorry.
So about the about the constants. So I have said like